Welcome to the course UEC 001. In this module, we will discuss a new topic, logic families. This particular topic is related to somewhere in digital electronics, and we will see how one can fabricate various digital integrated ICs using different logic families. So, as far as the introduction part concerned, we have to understand what is the actual meaning of logic family. So you have studied in the high school level course various logic gates, and these logic gates are available in the form of set of various integrated circuits, or simply known as the chips. So the set of chips that can be implemented for a different logic functions by any technology. There are some standard methodologies, which is known as the logic families, that includes some transistors and have some voltage levels for logic levels. Like there are two logic levels, logic 0 and logic 1. So there is a specific range defined for every logic family for logic 0 and logic 1 and for their power supplies. And these are the few parameters on the basis of which one can choose an appropriate logic family. So if viewers want to do a comparison among the different logic families, then these are the couple of interesting parameters on the basis of which one can take a judgment and select a particular logic family. So let us see the classification of logic families. So the very first part of the logic family is RTL, which is termed as the resistor transistor logic, and this is one of the oldest logic family, and nowadays not very popular. Therefore, we are not covering in this particular module. The second is the diode transistor logic family. Here, the combinations of diode and transistors in inclusion with resistance have been used, and this is also obsolete and not popular nowadays. The next is the TTL, which is known as the transistor logic, which is a sort of benchmark still. We will discuss this transistor logic in detail. Then next is the ECL, emitter coupled logic. For the high speed operations, this logic family can be used. And the next part is based on metal oxide semiconductors. So you can recall various types of MOSFET circuits we have studies in general can be broadly classified in PMOS and NMOS. So for high component density, this type of logic family is useful. And the last but not the least is the CMOS, which is nothing but a complementary metal oxide semiconductor. It is having a very interesting application, like for the circuit which required low power consumption, then it is always recommended to use the complementary metal oxide semiconductor logic family, that is CMOS logic family. And among the the sixth one, CMOS technology, is very much popular. So in this particular course, we will discuss the two logic family, TTL and CMOS, and we will see their applications. We will see how to design various logic gates with the help of this TTL and CMOS. But in order to discuss these two logic families in details, it is necessary to discuss various parameters to be used in different logic families. So we are starting with the first one, that is my voltage parameter. And let's start our discussion with this schematic. So over here, I have specified the two terms, output voltage range and input voltage range. And in fact, you can see that in case of my output voltage range, there is a range for output lower level, like this is my lower level and this is my high level. So this is supportive to logic 0 and this is supportive to logic 1. And for my output voltage, the range is from 0 volt to some VOL. That means the lower value of my output voltage. Likewise, the range for higher level is defined as VOH, the high level of output voltage, to the VCC. And usually we prefer this VCC voltage to 5 volt. Likewise, the range is defined for my input voltages also, like 0 to VIL, that means the lower maximum value of lower level for input voltage, and from 0 to this value, and likewise for logic 1 VIL to VCC, that means the lower level for high logic for the input voltage to the value of VCC. Okay, so now I am defining the term, that is VIH is nothing but high level input voltage, the minimum voltage level required for a logic 1 at an input. Similarly, VIL is low level input voltage, VOH is high level output voltage, and VOL is low level output voltage. And see one thing, for proper operation, the input voltage levels to a logic must be kept outside the unacceptable range. You can see that from these two schematic. Intentionally, we have kept the range of my input voltage is wider in comparison to the range of output. And soon you will get the answer why we are choosing this particular ranges. So these are the voltage related parameters, four parameters interestingly: VIH, VIL, VOH, VOL. In fact, they are suffix having the usual meaning, and one can easily understand the definition of all voltage parameters with their suffix. Now, the next important parameter is the noise margin. So as you know that in any real system, noise is always there. So in this digital IC terminology, what is the role of this particular noise? So it can add some random fluctuations to the voltage levels that we have just discussed. Okay, so we can define this particular parameter, noise margin, as the maximum noise voltage that can be easily tolerated by a circuit is known as the noise margin. In other words, it can be defined as the noise immunity of that particular circuit. So this parameter is very interesting, and we can check how immune my circuit is to that particular noise. In this DCIC terminology, we will express component noise margin in terms of volts, because we will determine this particular level in the voltage formations. So let us see the examples how to calculate this noise margin. So I have taken the same schematics that we have discussed in the voltage related parameters. This is for output voltage range and this is for input voltage range. So let us see the definition first. Noise margin is calculated from the knowledge of the voltage signals available in the output of gate and the voltage signal required at the input of the gate. What it means, now I can check. So this is the margin. The difference between VOH and VIH is nothing but this is the noise margin for my high level. So noise margin for high level is VOH minus VIH. Likewise, for the low logic, what is the noise margin? It is my noise margin for low logic is VIL. That means the input low level minus output low level. So this is the range of my noise margin for lower level. Okay. Similar to the voltage parameters, there are four current parameters, and again one can easily understand the functionality with the help of their suffix IIH, IIL, IOH and IOL. These are the high level input current, low level input current, high level output current and low level output current. You can just see this schematic and you can easily understand the concept. When level is high, that means output current can be moved from the output terminal to the gate. And if my level is high, then inputting to a particular gate is my IIH. If level is 0, then coming towards the output terminal is my IOL, and corresponding to 0 level, the coming the current coming from the input is my IIL. So you can check now the definition. IOH, that is my high level output current. It is current flowing out from an output when logic 1 state was there. IH is current flowing into an input when a specified high level is applied to the input. Similarly, IOL is my current flowing into an output when logic 0 state was there. And last, current IIL, current flowing out from an input when a specified low level is applied to that particular input. Okay, so these are the parameters related to the current. Now, this is a very technical parameter, the fan in. It represents the total number of inputs to a particular logic gate. So in general, we have seen the two input gates, but it is not necessary that gates will always have the two inputs only. Okay, it depends upon the applications. The gate can have the more number of inputs, but the counterpart is, as the fan in to a particular gate increases, then the speed of that particular gate will be slower. Similar to fan in, another component over here is fan out. And what is the terminology of fan out? You can check. This is a particular gate which is driving all these gates. So the number of driven gates by this driving gates is termed as the fan out to this particular gate. That means the number of output gates can easily be connected and driven by a particular gate is known as fan out to this particular gate. Okay, the maximum number of standard logic inputs that an output can drive reliably is termed as the fan out. In another term, all these gates will treat as a load to this particular gate. Okay, so in this schematic you can observe these 5 gates have been treated as load to this particular gate. So this is also known as the loading factor. And one can easily define the fan out, or one can easily measure the fan out from the current related parameters. So briefly I have given the statement. It is the amount of current available in the output of a gate and the amount of current needed in each input of a gate. That means the current which is available over here and the current which is required to drive this particular gate. Okay, so mathematically it can be defined as fan out will be the minimal value of the ratio of IOH upon IIH or IOL upon IIL. So idea will be more clear if we see one example for this. So we have selected the transistor logic for the fan out calculation, and the standard values are given over here: IOH, IOL 0.4 and 16 milliampere respectively, IIH and IIL 0.04 and 1.6 milliampere respectively. So you can check, we have calculated the term and this value will be minimal of 10/10 or 10. So the minimum value is 10. That means for this particular example, for the standard TTL gate, the value of fan out is 10. Okay, so my answer is 10. Now, what is the technical meaning of this outcome? Okay, so it means that the output of a TTL logic gate can be connected to no more than 10 inputs of other logic gates in the same logic family. So what will happen if one is going to increase? Suppose if one is going to increase this quantity beyond 10, suppose 12 inputs have been connected. That means the output will not be properly functioning. Okay, because the capability of a gate in case of TTL logic is to drive only 10 similar gates in the same logic family. So this is the meaning, the technical meaning of fan out. Another interesting parameter is power dissipation, and this is one of the key parameter for all logic families. The amount of power consumption is somewhere the essential part. Like I have told you in the last category, in the CMOS technology, it has a lower power consumption. Okay, so for a particular application where the power consumption is one of the key parameter, then one has to choose the CMOS logic family among the six logic families which we have discussed. So every electronic circuit requires certain amount of power to operate. This is understood. We have seen many of the circuits till now, and in this digital integrated circuit terminology, my submission is the power dissipation represents the amount of power needed by a gate. So for the proper functioning of a logic gate, the amount of power required is known as the power dissipation. Usually, we have the IC that includes four logic gates in the IC. For example, suppose if I am talking about IC 7400, which is the standard IC of NAND gate. Usually it has four dual input NAND gates. IC which has four gates will require from its power supply four times the power dissipated in each gate. That means if I am interested to find the power dissipation of the IC, then it has to be multiplied by four times the power dissipation by a single gate. So in general, formula for power dissipation is power equals to current into voltage. So average power dissipation will be termed as the average current multiplied by the DC voltage VCC. And the average current can be calculated as the average value of ICCH and ICCL. So what's the meaning of these two? You can just read the statements. ICCH is the current drain from the power supply when gate output is at high voltage level. Similarly, the ICCL is nothing but the current drain from the power supply when a gate output is in low voltage level. So interesting part is these two currents will not be same. It will depends upon what the level of gate we have selected, whereas it is at high level or low level. In both the situation, we have to calculate the amount of current draining from the power supply. Okay, in both the cases, we have to calculate separately the current drain from the power supply and take an average. Then we can easily calculate the power dissipation. Next parameter is related to the time. Okay, and it is related to the rising edge and falling edge, because we people are dealing at two logic levels, logic 0 level and logic 1 level. So there is a chance that there is a transition from logic 0 to logic high and vice versa. There is a chance of transition from logic high to logic 0. So one can define the term that is of rise time and falling time accordingly. So let's start the discussion with rise time, and you can check. I have defined TR over here. This TR is my rise time. So you can check, this is nothing but the time taken by the signal moving from 10% level to 90% of its peak value. So time taken by the signal when there is a transition from low level to high level, from 10% level to 90% of its peak level, is known as my rise time. On the counter side, on the reverse side, the amount of time taken from 90% level to achieve the 10% level of its lowest level while moving from a reverse transition, that means a transition from high level to low level, is known as the falling time. The propagation delay, which is related to the response. All gates have a propagation delay which is denoted by TPD, and this is the average of two switching times. So over here I have defined the two switching times, TPHL and TPLH, taking the average of these two, and this is my propagation delay. So their abbreviations are very much clear. TPHL means this is the propagation delay when there is a transition from high to low level, and propagation delay when there is a transition from low to high level. So you can check if this signal is applied, then usually we have taken the 50% level of this particular term. So the response from the edge, from the first rising edge, so you can check the time taken by this, the time taken by the gate to respond to this particular input from low to high. So my output is moving from high to low. So it is propagation delay from high to low. Okay. And accordingly, when there is a falling edge, so according to this particular edge, what is the total propagation delay taking? The average of these two time is nothing but my propagation delay. So this is all about the various parameters. So in the subsequent module, we will discuss about the designing of different logic gates in TTL and CMOS logic families. Thank you.